Hypothesis test with larger samples, example 8. You flip a coin n equal 20 times and the coin turns up heads x equal 11 times. Thus the proportion of heads in the sample p hat 11 over 20 is a fraction. 11 over 20, if you divide 11 divided by 20 is 0.55. So the proportion of heads in the sample 0.55 or 0.55, and we want to know if this sample provides sufficient evidence that the coin is unevenly weighted. So there are slightly more heads than tails, but that could have happened just by chance, even if the coin is evenly weighted. So we want to do some hypothesis testing and compute some probabilities here. So for this purpose, we need the null value, which is the proportion of heads we would expect in the long run if the coin is evenly weighted. So if it's evenly weighted, we expect it turns up heads half the time with 1 out of 2, or it's a decimal. 1 divided by 2 is 0.5. And so that's P0, that's the null value. Q0 would be the other null value, that's the proportion of tails. 1 minus P0, or 1 minus 0.5, is also 0.5. So we expect if the coin is evenly weighted, that it would turn up heads half the time and tails half the time. We like to test hypotheses. The null hypothesis H0. If the coin is evenly weighted, we expect that P is equal to 0.5 in the long run. The proportion of heads in the long run should be 0.5, and that if the coin is unevenly weighted, we'd expect the proportion of heads to be not equal to 0.5. This is a two-sided test. If there are either more heads than tails or fewer heads than tails, then we would say the coin is unevenly weighted. We'll set our significance level is at 0.05. That's the probability of making a type 1 error. The probability of rejecting the null hypothesis if the null hypothesis is true. That's a common level of significance. Some researchers like to use alpha equal 0.01 if they want to be very careful about not making a type 1 error, or maybe 0.1. So it's a little bit arbitrary, but we'll 0.05 is a common level of significance. So we want to check whether n times P0 is at least 5 and n times Q0 is at least 5. So P0 and Q0 are both 0.5. Our sample size is 20. So 20 times 0.5 is 10, and that is greater than or equal to 5. So that's a yes. Q0 is also 0.5. N times Q0, 20 times 0.5 is also 10, greater than or equal to 5, and that's a yes. So we got yes, yes. That means we can proceed to the next step and use the compute the z-score and so forth. Otherwise, we would need to compute the exact binomial probabilities, such as the tree diagram, which we had done with some of our examples. In order to compute the use a z-table, we need to find the null value and the standard deviation, or the standard error. So the mean of p hat, on the average, we accept the sample proportion to be 0.5 if the coin is evenly weighted. That's the null value. So the mean of p hat is 1/2 or 0.5, and the standard deviation of p hat, square root of P0 times Q0 over n. That's going to be 0.5 times 0.5 divided by 20. And then we can put those into the calculator. That comes out to be 0.111803399. We do the square root key and then 0.5 times 0.5 divided by 20. Okay, so then we can compute this test statistic. That's actually a z-score. The z-score is the score minus the mean divided by the standard deviation. It's the same, basically a variation on the same formula that we were using earlier in the semester. So our score here is the sample proportion, which is 0.55, and the mean of p hat, if nature audit true, is 0.5, and standard deviation we just computed was 0.111803.399. And so do the subtraction first, and then divide, and this comes out to be approximately 0.45. So our test statistic, or z-score, is 0.45. So this can also be abbreviated. So, it's kind of a shortcut abbreviation. Instead of putting in our subscripts here, P0, Q0, we can just write P hat minus P over square root of P times Q over N. And P, in this context, P is going to be equal to P0, so it's going to be the same formula that we had before. But it's just a shorter way of writing the formula. So you'll see that in some textbooks. Instead of, if you want to be very careful to indicate that we're actually using the null value, if you want to make it absolutely clear we're using a null value here, you put in the P0 and the Q0. Here, this formula is a little bit ambiguous because it's not really specifically specifying the null value, but it's less handwriting to do it that way. So if it's clear that you're using the null value, you don't necessarily have to put the P0 and the Q0 in the formula. Okay, so so the next step is to look up the z-score in the z-table, because of the way our table is set up, we want to use the negative side of the table. So we want, because we're doing a two-tailed test, we actually have to multiply that number by 2. So we want the probability of getting a z-score that big if h naught is true. So we want the probability that z is either greater than 0.45 or less than a negative 0.45. So this would be the right tail. So z-score of 0 is in the middle. 0.45 would be on the right tail here, and negative 0.45 would be on the left tail. So we have 0 in the middle. The left tail is negative 0.45. That's this probability here, but the bell curve is symmetric, so the left tail is going to be the same size as the right tail, and our table is the way, because of our way our table is set up, it only gives the left tail. So we want to look in row. Well, let's put my 0 here. Want to look in row negative 0.4 and column 5 of the z-table, and then multiply that number by 2. So it's going to be 2 times the number we get from the table, from the z-table, get 0.3129, and then multiply that by 2, because we have we want to include both tails here. So it's 0.6528. So that's our p-value, and it's more than our level of doubt. Alpha is 0.05, so we fail to reject h naught. there's not enough evidence to say the coin is unevenly weighted. And that concludes this presentation.